Hi again, everybody. Here we are again. And so the topic of this video is now going to be discussing solution concentration. Since chemistry is a quantitative science, and so much of what we do, so many of our experiments and various things we do in a lab do take place in aqueous solutions, we need a way to identify how much of our solute is actually present in those solutions. And that's where this idea of concentration comes in. Concentration is the amount of solute per volume of solution. Concentration can be measured in a few different ways, either using something we call colorimetric methods or different quantitative methods. The units of concentration vary depending on whether they're based in mass or moles or maybe even volume, but concentration is always expressed as a ratio. And so you might have something or you might have concentration in terms of mass per volume. And so mass of our solute per volume of the entire solution. Or you might have percent mass to volume. And so just the same as mass to volume, but expressed as a percentage. We also have moles per volume. So moles of our solute per volume of our solution. We can see the units over here, moles per liter, units of mass to volume, MV or percent MV. Or also equivalents per volume, equivalents per liter. And we'll talk about all of these and a couple other different ways to measure concentration as we go on. All concentrations that, at least that we talk about in here for now, are going to be defined in terms of the volume of the entire solution. And that's important to keep in mind, is that when we talk about the volumes of solution in here, the second part in our ratio, that's the entire solution. So both the solute and the solvent taken together, not just the volume of the solvent. And so for instance, and again, we're going to look at some other examples of this as we go on, but if we have something that is maybe a 2 molar solution, so 2 moles per liter, then this is 2 moles of our solute over 1 liter of the entire solution. And so that entire solution, remember, is our solute plus our solvent, the whole entire thing. So we have to keep that in mind as we're working through this. When we're looking to make solutions of very specific concentrations, we use something called a volumetric flask. And so here's an example here of a 50 milliliter volumetric flask. You probably can't see it on your screen, but there's a little line right here on the flask. That line marks 50 milliliters. So the way we would make this solution is we would do some calculations to figure out exactly how much of our solute that we actually need. So we can see that that's been measured out here. We put that into the flask before we add in any water, or maybe we put a little water in there to start out, but certainly not much and well below our line. So now we have just our solute in there. Now we add water until the total volume is up to our 50 milliliter mark. And so now this whole entire solution here contains both our solute and our solvent. So that's important to note. So a mass to a volume concentration, some examples of where that's used. The concentration of blood solutes, very often reported as a mass to volume, usually micrograms per deciliter. And so if you're looking to find just the amount of things in blood, those would quite often be the units used. Percent mass to volume concentration. Concentration of IV solutions, very, very, very often used in percent mass to volume. And so some examples down here, we have, for instance, a 0.90% NaCl solution. And so that's 0.9% NaCl compared to the volume of solution. And so just the name of that, if you are in a medical setting, that's a normal saline solution. So when somebody says, or if you're watching some, maybe Grey's Anatomy, or if you're old school watching a little bit of ER, and they say, hang a saline solution, this is what it is, 0.9% NaCl solution. Or a half saline solution, 0.45%. maybe a 5% dextrose solution. So again, that's 5% mass to the volume, 5% dextrose compared to the whole volume of solution. And so an example of that, and you can see how that would work out here. And so it would be your grams of solute per milliliters of solution, and then to convert that to a percent. But in the case of the 5% dextrose, then in that case, you're going to have probably like 5 grams of your dextrose to 100 milliliters of the solution. That's how it would be made. 5% dextrose and the 0.9 NaCl. We see the name for that here, a D5NS. Or, and I'm not sure what this one would be used for, this lactated Ringer's solution. But we have some NaCl solution in there, some sodium lactate, some KCl, and some calcium chloride. Some of you who maybe worked in the medical setting, you might know what this is. I don't know what it's used for, but I know how to read that because I know how to read concentrations. For very dilute solutions, and you see this actually more often in environmental applications as well, if you're looking to maybe look at how much arsenic is in your well water, maybe, very common thing that's looked at in Maine. We use ppm and ppb for our units. ppm and ppb still really is a mass to volume percentage, only now, so we can see, so we'll multiply by 100 to get to our percent mass to volume. We're going to take our grams of solute divided by milliliters of solution, and we're going to multiply that by 1,000,000 to get to ppm. Grams of solute divided by milliliters of solution times 1,000,000,000 to get to ppb. And so that would mean, for instance, that if you had a some sort of environmental contaminant that was at 5 ppm, that meant that if you have 1,000,000 overall particles, 1,000,000 particles of water and whatever else might be in there, out of those 1,000,000 total particles, 5 of those are going to be that contaminant. And that's what ppm really means. Quite often in chemistry, we use molar concentrations. So the moles of our solute divided by the liters of solution. This is one of the reasons why it is so important to be able to convert from grams to moles. Remember, using the molar mass. And so, for instance, you might need to know the molarity if you, let's say, maybe dissolve 2.3 grams of NaCl into enough water for a total of 250 milliliters of solution. The first thing that you would have to do is take that 2.3 grams of NaCl and convert that over to moles of NaCl. You would then take that number and divide it by the liters. Now this is given at 250 milliliters, so we would have to convert that to 0.25 liters. And we do that calculation out, and that would tell us the molarity of that solution. And so it's always the moles divided by the liters in order to get to our molarity. Quite often blood tests report in millimoles per liter. So we'd have to have an idea of what that is. Electrolytes are actually reported in terms of units of charge. And so one of the whole ideas of electrolytes is getting those charged species in there. And so it's not only important for us to know how much of the actual ion is in there, but it's important for us to know how much charge that delivers as well. And so to find equivalents per liter, we calculate our molarity by the charge. And so let's actually work through an example of that here. Let's say that we have a calcium chloride solution. What we do for this solution is maybe we dissolve 0.75 grams, can't spell the word enough, in enough water to make 750 milliliters of solution. And we want to know what the concentration is in equivalence of our Ca2 plus ions. So the first thing we need to do is to find our molarity of this solution. So we're going to take our 0.75 grams and we're of CaCl2, and we need to convert that over to moles. And I haven't actually done this out yet, and so let's see. I'll use my trusty periodic table behind me. Calcium molar mass of 40.078. So we see why this was so important to be able to convert grams to moles again, like we talked about a couple lectures ago. Chlorine 35.453. But I have 2 chlorines in there. So my molar mass of CaCl2 we see some dimensional analysis coming up into play here. So I do this calculation out, and I see that I have 0.0067577 moles of CaCl2. Now you'll note that I pretty much ignored significant figures. You never want to round for significant figures until you're done with the calculation, and we're not done yet. And so I'm not rounding this off at this point. What I am going to do now, though, is take that number of moles, 0.006577 moles. I'm going to divide that now by my volume, but I need to convert that over to liters. So divided by 0.75 liters. And I get a molarity of 0.00901. I round to 2 significant figures because that's how many I had in my measurements. So molarity of 0.0090 molar. We use a capital M to depict molar. We're not done yet, though. So remember, we wanted to know the equivalence for our Ca2 plus ions. So now I'm going to take this molarity and multiply that by the charge on a calcium ion, which is 2 plus. So I'm going to multiply this by 2. And so I get, and if you're chastising me and saying to yourselves right now, you should have been able to do that in your head, Mr. Staples, you're absolutely correct. So I get a final answer, though, of 0.018 equivalents per liter. And that's how you would do out that entire calculation. Very often with solutions, we also have to do calculations involving dilutions of them. It's very common to have to dilute a concentrated solution down. So a great example of this would be something like hydrochloric acid that's used in the lab. We will use molarities in the lab of maybe 1 molar, 0.05 molar, so some fairly low concentrations. It comes to us in a bottle, and we usually store it as concentrated hydrochloric acid, which, if I remember right, has a concentration of 12 molar. And so we would need to find a way, or we would need to know how much of that 12 molar to use to then dilute to get the concentration that we were looking for. And so we use this dilution equation here. C1 times V1 equals C2 times V2, where C1 equals the concentration of our stock solution, whatever we're starting from. V1 would equal how much of that we want to use. C2 equals the concentration of our dilute solution. V2 equals the volume of our dilute solution. And so typically with this sort of calculation, here's our guidelines and our steps. We always begin by seeing which of those 3 variables we actually have. You'll always know 3 of those, and you'll be looking for a 4th. Rearrange your equation so that the variable you're trying to solve for is isolated on one side, a little bit of basic algebra here. Substitute in the supplied variables and solve it. And so again, let's look at an example of this. So let's maybe stick with our 12 molar concentrated hydrochloric acid. And so in this example, we want to prepare maybe we'll say 250.0 milliliters of 0.05 molar HCl from our 12 molar stock solution. So the thing that we need to know, we're going to use our volumetric flasks that we talked about a little while ago. Very crude drawing of one here. Actually, that is not bad for my artwork. What I need to know is how much of the 12 molar HCl do I need to actually dump in here so that I can then eventually fill it up with water up to my 250 milliliter mark, which would then give me 250 milliliters of my 0.5 molar solution. And so we're going to use our M1V1 equals M2V2, or sorry, C1V1, C2V2. And I sometimes just use M1V1 because that's its molarity, but same thing either way. So C1V1 equals C2V2. And so let's look at what I'm looking for here. I want to prepare 250 milliliters. That's what I'm going to end up with. So that's my V2, 250 milliliters of 0.05 molar HCl. So there's my C2 from a 12 molar stock solution. So that's my C1. So V1 is what I'm looking for. That's how much of the 12 molar that I need. So I'm just going to rewrite this. I'm going to divide both sides by C1. So I get V1 equals C2 V2 all over C1. So now I just plug that in. C2, my 0.5 molar. V2, my 250 milliliters, all divided by my C1, my 12 molar. I get out my trusty calculator, 0.5 times 250 divided by 12. I get 12.4 milliliters. Let's see how the units worked out. Molars canceled out. I'm left with milliliters, milliliters, and that's good because I know that's what I was looking for. So again, what this tells me is that I want to take 10.4 milliliters. Got my volumetric flask here. I'm going to take 10.4 milliliters of the 12 molar and dump that into my flask. So now I've got a little bit of the hydrochloric acid down in here, the concentrated stuff. And then I'm simply going to add enough water in here to get up to the 250 milliliters. And so then at that point, I will have 250 milliliters of a 0.5 molar solution. So that would be how we use our dilution equation. You'll also see concentration or work with concentration when it comes to dosages. And we're going to look a little more at that in the next video. So actually, I'm going to hold on to this one because that will be the topic for our next lecture. And so as far as concentration goes, that's the way the cookie crumbles. Have a great day.